I'm going to talk about a topic that I've been working for some years, but very intermittently, because it's quite strange and difficult in some sense. So, to describe several things which we have done during the years. This is in collaboration with Luis Lerner, Marcelo Rubio, that was here at some point, and Pablo Montes, which is my last student in this area. She's still working, he's still working, finishing his PhD. Okay, I'm going to start talking about the motivations for doing this. And then I focus on the formalism, why these fields appear, how, what are the properties. So we are going to conclude about the analytical part, some things, and then I'm going to spend some time in the numerical part of this, which is, it took a while for us to really evolve numerically these equations, but now we are thinking that we have some success. The field is getting mature to be able to use these equations for astrophysically relevant situations. Basically, these are the two papers that we have in this specific thing of the conformally relativistic theories. One is analytical and describing the theory, and the other is about the first numerical sense we did in 1 + 1. Now we are doing in 2 + 1, having all the machinery to do 3 + 1, but we haven't done it yet. So why to look at the conformal class? Well, because this is sort of interesting because at very high temperatures, the particle masses are almost zero compared with the energy of the particles, so we can treat them as massless, and then they are conformally invariant. There's no more length scale. And this is important either at the early cosmology, in gluon plasmas, and I should add that there are many situations in astrophysics where they say you have a plasma, electron plasma, the temperature is very high, and so you also are very close to the conformal regime. And radiation, of course, is conformal. But there is another reason, and this is because the conformal class is very small, so we can study in detail. Because the rest of the zoo of divergence theories is very big. There are many, many. And so when you try to investigate them in some, either numerically or analytically, there are many cases. You don't know what to do really. So this case is very particular, it's very small. And so we can study, we can have some hope of studying it completely. So that to me is the main reason to why I'm looking at this. Well, this is a short story about the field. We have some pointer.
Where's the stick? Where is the stick?
Yeah, it's there. Oh. So we have early on some theories. And they proposed some theory that was basically take Navier-Stokes and do it covariant, to put some indices there for dimensional things and say, okay, these are the theories. But then Hitchcock and Lindblom showed that these theories were really well ill-posed. Because if you took some velocity field that was not surface forming, you will get into trouble. That we understand today, but at the moment it was. But just early on, we have some, because basically these two theories are, in spirit, they are parabolic. And we know that parabolic means that we have some preferred time slice, and so general relativity we don't, and we have infinite propagation beta, general relativity we don't. So we want to do better. And so there were some proposals with basically this proposal is the one that was taken by the after some work like this and put in all this in a nice fashion to discuss this work. And then we have some much more modern work from this decade on other type of theories which are also divergence type, but they are second. The ones I'm referring first. It seems to be okay. It seems that they are well posed. And we are going to compare, like basically what we did numerically was to compare how they behave compared with ours, the divergence type, and they are basically very similar. So the behavior is quite similar. We could reproduce basically the same things that they have. When I mentioned they, it's pretorius, pretorius. So let's start with the relativistic factor fluid. You have a particle number, which is some vector u, and you have the energy moment intensity, this form, where P is a function of the energy density rho and the particle number. And you just look at these two equations and solve for this of u and n rho. So this is the perfect fluid system. And if you look at the equation, this equation, you notice that this form here tells you that you can find another function S such that therefore we have, when we take the divergence of S, we get some conservation, which is independent of the others. And this is quite general from divergence type conservation. You get an extra conservation. You have it zeros here. If you don't have zero, it's not. But there is some divergence of some other quantity, which is because of the equation, it's an equation. So there will be something here, but that's not the answer. Source. So this is what we know very well from perfect fluid, and now we want to put some dissipation to add more fields. And this Jerry, etc., and what they did was to add another equation from some sources, and you require that this is symmetric in the last series and it's trace free. And then when you find also that there is an entropy because there is an idea, some source, and you can choose the way that is seen as possible. So you will be creating entropy along the evolution. So look at the amount of equations. You have one equation here, you have three equations here. What is the dimension? These are this amount of this quantity of equations. And so if you add this will give you this number plus this, because when you add this. So you might think of these equations to be equations for 10 and 8. So you have more equations, but the degrees of freedom hidden here are the particle number and energy momentum tensor. And that's why there was a way people thought about this, so that really your equations are for N and T, and there are more equations, and how you find the more equations so that you have equations for every one of the variables. So you say, okay, this A has to be a function. And then you propose that this is the way they build the theorem. This, okay, now we want an entropy. We want to have an entropy, and we want a low entropy law, so that the divergence of this entropy is growing. And here I put this because the importance of having conservation law is because we expect to have shocks, right? Because it's a hyperbolic system, generic and degenerate. Not degenerate, so you expect that even smooth data will produce shocks. And if we are going to deal with shocks, we need a system of conservation law so that we can make sense of shocks mathematically and numerically. So it's good to have a system in conservation. Right? Otherwise, we don't know how to compute anything. And we don't have a theory also analytical. So if you want to have an entropy law, then find out that to have this two, you need to the N, you need to have a function here of these three values. Some these are sort of internal values, no? So that they appear as Lagrange integral. So that N, T, and A, ABC, they are derivative, second derivative function. But that's a consequence, it's a theorem. If you want to have an extra conservation law growth, no? Then you need to have this quantity, this insert quantity have this structure. Coming from some, at least locally, coming from some function on this field. So that's what one uses. And the idea is to have a generating function which has orders. This order has only psi and psi is a scalar that is associated with part element that is a Lagrange multiplier associated with it. And then we have another scalar here, which is the normal psi. So this function, we say it's a function of these two scalars. And then to first order, you put a function, say that, but here you have a new this. So it's first order in this variable second. And then you continue. This one is a function of these two variables. And then a function of psi, which is second order in this variable, and the scalars to come up here. You have this one, the trace, the contraction. You contract with the psi v, you contract it twice, and then you take the square. So we have this, these are the scalars that come in. This is at the second order the most general generating function. Right? And you see that there is a lot of freedom here for function. Any choice of this function will give you a second order theory. First order will be your perfect fluid, some equation state. This order will give you some constitutive relations, like saying that the heat flux is proportional to the gradient of the temperature, and so on. And this is going to be what will give you the hyperbolicity of the equation, the second sounds that the other comes. So this is what I just said. Well, this is a form, the general formalism. What do we know about this? Well, you can make it hyperbolic. You choose this psi 2, the second order term, in a specific way. I mean, there are a lot of freedom. You can get that they are hyperbolic. You have a symmetric hyperbolic system of equation. So life is nice, it's well posed. You get near Navier-Stokes behavior around equilibrium. That is, if you perturb slowly, then the solution you get, if you plug it into the Navier-Stokes, the error you make is small. That's what you can know, because things decay very fast. Even if you put arbitrary data, small data, it will decay fast. There's no concept. Although the Navier-Stokes, which in this case will be Eckhart or Landau, there is ill-posed, so it's not really an equation you can solve. But the error, the fields will satisfy this equation too, I would believe, but they are not exact. We have global existence for small data. That is because what happens is that this dissipation acts on the whole set of equations. And so if the data is small, they will drive it to equilibrium. And we know that there are shocks for sufficiently large data. And so we know that to deal with this system numerically, we have to do something where we have shock capturing methods. That's what we know.
Oscar,
Yeah.
can you evaluate the previous quantities with some energy conditions? Or, I mean, what I'm trying to figure out if the energy conditions can, where did they get in this picture, or they didn't get it all?
You mean the energy conditions like the TAB
Yeah.
conditions? I don't know. I haven't looked. So what happens there? This is the whole zoo of divergence theories, right? It's huge. You have basically three functions which are free. You can adjust the first. You say, okay, I want an equation of state. That's okay. You can adjust the second, saying, okay, I want that the heat flux is proportional to the gradient of temperature in some way with some coefficients. Okay. And then you have these other functions of these three quantities that we don't know. Right? And they play an important role. So it's too big. I mean, if you start doing numerical things, if anything you do, it takes some time and cannot explore all these parameters. So what we look is was a conformal. So we went to the conformal class. Calling the conformal class means that we are going to change the conformal class to a positive function. The connections between these two methods are related this way, where it sees this. So for instance, if we take the divergence of T in one of the connections, calculation, you get this. And you see, this here you can, this n here is the gradient formula. So this you can absorb by changing the weight of the key, saying the key goes to like omega to some part. Right? So you can absorb always this term. And so we know that the theory will be conformally invariant for some weight for the key if the trace is zero. And that's it. That's a condition. So your T's have to have trace zero to all orders. And the same is going to happen for them. So we just took out this particle number conservation because in many cases, like photons, etc., you don't have conservation. So we just took out to simplify that. So we are going to deal with this question. So the first we know we need is TAB to be trace free at the order. And what you get, But the equation for the ABC is that has to have this form where this contraction is down. And actually what it implies basically is that this A is totally symmetric and trace-free in any index you take. So it's very similar to the TAB. So total symmetry and trace-free in all the indexes. And so you put this in the generating function, because recall that T and A are just derivative of the generating function. For instance, if you want the first part, the zero part of the PAB, and the factored part, you get this equation, so there is a relation between these two functions. This is zero, so it doesn't. So you have a relation there. And if you put the trace equal to zero, you get this. And so this function here is actually this some constant divided by the temperature to some power. That's it. There is only one constant as a free constant. And really this constant doesn't play any role because it's just multiplying everything, scaling everything. So here, so you can subtract. So there is no freedom. Right, for instance, if you define the P of this equation like this, then you find under rho, the same way you find that you have the equation state of radiation for equal to 4, rho is equal to 3. And this mu becomes 1 of the square root of the temperature, and the side divided by r for velocity of the fluid. So this is the contact. If you go to first order, you get this equation for the T, and this equation for the A, and you get again that the function is totally determined. There's just some constant value to somehow, and that's it. And that constant this constant can be absorbed also changing the size between the vector psi A and the vector the tensor psi A. So you scale them, that constant you can put it equal to 1. So there is no freedom up to there. If you go to second order, you get these two set of equations, 6 equations, and that fixes everything. You get this equation that fits the 3 possible functions, and so here you get how each one of them behave, and then there is the relation between one and the other. So here you have this one with 1, you get 2. So everything is fixed. There is only a single constant. So they are all related like that. And so we have a 1 parameter function. All constants are fixed. And so the question there was, well, this thing we have is hyperbolic or not? Because it could have happened that the sign of these things were such that the system is not hyperbolic. Because for hyperbolicity, this second part of the second order function has to be convex. Right? And if you have 3 directions, it could be that it was a saddle. We didn't know. So we look at this and we find that it indeed is symmetric hyperbolic. So this is a condition for this. So there are nice theories. I was surprised. A nice set of theories to play around. This is this expression times this. You can see that it's 4. See that this is also that when you change the psi a b, it will give you a paraboloid. This minus sign here is okay because it's with the wrong sign. It's a contraction of 2 4-dimensional vectors which are time-like, so it's a minus. So we have that. So these theories are nice, and then we say, okay, we want to do it numerically. We want to study this. So then, conclusion of this, we find that the dissipative relativistic fluids accommodate for conformal fields. So you can have a conformal fluid being there. We have I show one of the parameters, this discussion, that's a parameter that enters in the generating function. Then there are 3 more in this IAB that I wrote, which are the sources. Then there are 3 parameters there. They are basically the sign of them is defined so that the entropy grows, but the size is free. You don't have any control of them. They will give you some constitutive relations, what is the heat conductivity, etc. But in general, they are free. So you have to study how they behave. So if you choose a parameter for the second order piece to be big enough, the system is composed, and you can run into the computer. So we now go to the numerics, and the first thing we want to do is
So you said that that basically the equation of state for these conformal fluids is that of the radiation,
yes.
right? So, but does that mean that the fluid always moves with the speed of light?
No, it moves to 1/3 of the speed of the speed of the fluid square is 1/3, right? Because that's the speed that it moves.
Sorry.
So
Can that speed be modified, or is it given?
which one?
The speed you're talking about?
It's fixed. And in equilibrium, right? When you put the variables, so you take second derivative, but you evaluate in equilibrium, you have this speed. And then there is a second speed, which has to do with the other modes, and there is a unique one. And this is square root of 5 or 3/5 or something, and it's fixed. So you cannot. So we wanted to compare these theories with the similar theory in the EMK branch. Because there was a paper by the producers that there are actually a couple of papers where they did the first simulation 1x1. So we wanted to compare to see whether these were things which are very different or not. And the idea was to start preparing this, to understand and get some knowledge and some technology to apply to astrophysical problems. We want to see what we could do, because as we see, there are some things that are. There was another point that if you come from the conformal theories that people do from field theory, they don't have a heat current. It's only shear. And they justify it and say, well, you should find out that your heat current is 0, etc. And we don't. You can show that if you set the current to 0 initially, it will not stay 0. So you are there with current, with a heat current all the time. So we want to see whether numerically we could find somewhere, some region, some parameter where this current could be set to 0. There is some strange thing in the middle that we found, but we couldn't get rid of this heat count. And so, and that has to do with this, and we want to understand the theory, and maybe we do enough computations and be careful with the scenes so that the runs, etc., you find some new things. And there are a couple of things which are interesting. So how do we do the time evolution? We take this component, on the 0 component of the conservation law. So we do discretize this in space, discretize them in time. But notice that this TI, A, and B, which has space type in these things depends, I mean, the generating function give you these things in terms of these variables, these abstract variables that are hidden there, the multipliers. While we are solving for this, so we have to do at every time step, we have to get a map from this with these variables, we can say here for the next step. This is common in hydrodynamics, relativistic hydrodynamics, you have to do the same. But here is sort of a big system. It's not in hydrodynamics, you have to solve one equation like that. Here you have a system. You can solve some, I mean, it's just a version of a matrix, but depends on the other quantities. So you have to do it in any case implicitly. So we just do a Newton-Raphson method. So the time steps are like this. You get these two values of all the t's, the TA and the in. Run a time step, compute these ones, at t plus equal t, and then go this not to this one, at t plus eta t, back here, I here, and run space. So it takes a while because you have to solve in the middle of Newton-Raphson iteration for every point in your grid. Right? So it's we have a code, it's written in Julian, time stabilization, so the root of conformally. In space, there is job capturing method, it's Zeta bueno method, which is quite good. I find that this is really nice. We have to use Newton-Raphson for the value of the map from variables to variables. And we use extensively the symbolic part of Julian. Why that? Because at the beginning we just say, okay, we write the code in C and run it. And Marcelo did it first. And the code was extraordinarily slow and we had problems. And there were mistakes because the equations are huge. And this inversion is huge. You have to compute the Jacobian. And it's a mess. So what we did at one point is to say, okay, Julia has a symbolic part. So the equations you use in the code, you can say, okay, declare the variables to be symbolic, and then you can take derivative in a symbolic way. Do everything symbolic. With the same variables you are using to run the code. And this is very good because then you can check. Right, you have the code, the variables say, okay, this should be symmetric hyperbolic. So if we take a derivative of one of the equations with respect to some variables and the derivative of another equation with respect to another variable, we should get the same. And so you can check the whole system. You can look at the propagation speeds, everything analytically or semi-analytically, just compute the eigenvalues and vectors. So this was very good. Here are some results for two cases. This was a Gaussian of probably some polynomial in some region in zero. And this in the actual code is scanned with a double part. It's a periodic, so I'm showing. And this was shock. And you see the spread of the shock. And in black is the Euler part without dissipation. And here there are three choices of one of the coefficients. This is the coefficient of one of the i's. And you see that there are a lot of difference. And you can see that there are some extra shocks coming from the other propagation speeds. And you see this new value, this was one of the scalar, you see, because it's basically a derivative because of this first order term, you relate derivative of some of the fields with the fields. And so if the field has a shock, this derivative will acquire some spikes. And you see the spikes here.
This is the result after evolving for some time.
Yes. Yes.
And what was the initial condition?
This was a block like this,
Oh, I see.
and this was something.
And it just was moving towards the right.
Yeah. So you see in this side, you want these spreads and this screen shock. And here we have put shock. Check. So it's don't expect to understand much of it. Just show that the code runs, and we got similar results as the other theory, the NK theory. So it's really simple. We could get the same profiles. So it's doing something simple for some parameters. So we could adjust our parameters to get to the blocks they have, and they look very simple. So in a sense, there is some similarity between the two theories, at least for this component.
So you have a kind of physical argument to say why the solution space for this equation should look similar to that one.
Well, I guess the conformal speeds, I mean, this propagation speeds must be the same. So you expect something simple. The difference, as far as I understand of these two theories, is that they don't have a perfect entropy law. The entropy law that they use is valid up to some order, not up to the sort. That's why they can get away having a theory which is not this one, because these are basically unique. But there should be a lot of examples. So we expected this.
But then you'd expect that the some types of initial data actually with the solutions would differ a lot in kind of.
Yeah, with the entropy, with respect to the entropy. Yeah. That would be nice to check. We should get together with them and try to fix some data and see what we do. But the ones they should have in the paper, we could reproduce. So, so I said that we use a lot of coaching. For instance, these are the propagation speeds. This is the sound speed, and this is second sound speed. And symmetric, that there is a zero mode too. And this plot is just we changed the u, the velocity. We did a Lorentz transformation just to see that we get all the velocities going. We do a Lorentz transformation to the opposite direction, and then all the velocity should go to one. And we did that because there were many terms with the velocity, and we want to check that the Lorentz transformation was good. And that way we discovered some mistakes also, of course. And so this is checking. It's nothing profound, it's just a Lorentz transformation. But in the equations. And we also check the symmetry. But now what we did, because we wanted, this was a 1+1 code, and we wanted to do a code 2+1 or 3+1. And the equations are huge. So what we did was to numerically put a generating function that we know and generate the whole code and just use it as it comes from there. And so, for instance, this computes this derivative. And here, notice that this mu here is defined not as a function that we put mu is equal to psi a square root, but we say we have this function mu, and the derivative with respect to psi a is this. So we don't put the function. Why not? Because if you have one of these functions, huge functions, the symbolics will go and replace everywhere the mu for what you say that this was a mu, and the code then explodes. This way we say, okay, mu has this derivative, we take the derivative and we keep the mu's as something you put in the code. And then when we have to evaluate, we just first evaluate the mu and then put the number everywhere function. That's why we concentrate, connect this. For instance, here, you see we are doing some derivative of this guy function divided by 0 divided by. And then we build a function. So this function will be built in Julia in a very efficient way. So if you have threads or you have a MPI, etc., you will create build a function that you can parallelize and do all sorts of optimizations in theory at least. So that's why we use this sort of things. And here, for instance, we can do well. Just this is a Jacobian with the derivative of C over an L. This is a Jacobian for the transformation between the conserved abstract variables. So Julia just computes the Jacobian, and we use it. Compute the Jacobian and evaluate the function, numerical function, and then we put that function in the code and Jacobian of the Newton ramps. So we don't need to touch these things because they are huge expressions. There is a lot of, it's a big, huge vector. You have to do the Jacobian of that thing and invert it and so on. So you don't want to know anything about it, just do the numerical. And as I said, you can use CPUs, etc. That's what they promise. Some things are implemented, some things are not. But at least if you do that, and you wait sometimes, they will be okay. So here we have some plot of the 2D calculations. That's to show that the things are running. Really. This is a 2D fluid coming from a node here getting to the space. And it has, so far it has a flat metric, but we are doing now with the arbitrary metric and Christoffel symbols connection, so that we can implement the code directly with the just so it should be working before Pablo's thesis. So let me conclude. So we have a technical part. We can explore the simple space of parameters. The equations are complicated, worse than we thought at the beginning. The symbolic tools were very important to make codes in any dimension and to check that there are many things like propagation speeds, etc., that you need for the part of the code. These Bueno systems, they need the maximal propagation speed. So it's good that you can compute it numerically and put in the code the right propagation speed. So this is another part of the symbolic zone. And I think now we more or less have a mature understanding of this. So maybe we can start doing astrophysical things with these fluids, which is really what everybody wants, but nobody tries. I guess nobody tries because it's hard. To implement this numerically in astrophysical environment takes some time. But so we hope that since we'll be planning the future. Thank you.
What astrophysical scenarios are we going to consider first?
First, an accretion disk. Because there we should see something, you know, these accretions disks, they get very, very hot near the inner circuit, inner boundary. So that's what we first want to understand.
So you said you get very complicated questions.
Yeah.
How does this compare with the targets?
I think they are simpler, yes, with the second order system. So it's more compact. But I don't know details. Just look at the paper and what they put there as equations, etc. Seems to be very simple. So maybe they are better for this.
What's the downside?
I don't know. The downside is this system seems not to have an entropy in the same way these other systems. So they might run out of the validity region, etc. But there are many reasons that maybe they run out, like this will run out, will be perfect, will conserve entropy. The entropy will increase, but it will be out of the also of the validity. So I'm not proposing one of them. It's good to have several before we didn't have any. So.
So you use conformal variance to impose some conditions.
Yeah.
But do you use a conformal factor?
No.
No. So it was just first.
Yeah, it's to
this,
just to
but
select this branch, and it's nice because otherwise, when you try, you say, okay, I want to do numerics with this. There are so many theories, so many parameters, functions, and somebody will say, well, put here this and put there this other thing. Should that you got too many. And there are some problems I didn't mention, but for instance, this Jacobian, where we do the inversion, there are some point in the parameters, the chi2, this parameter, where it is no longer inverted at some point. So we have to be careful with these things. So
Are those points going to be analog of the vacuum state in standard geohydro?
no, it's one parameter. It's chi2 has one value for which it's not possible to invert. There is a collapse on the eigenvectors. And we saw, okay, maybe this value of the parameter will give me a theory with less variables, so that we can get rid of this heat current. But now, if you look at the theory there and that point, it's still covered some heat current. But it's something we don't. So there should be a smaller theory at that point.
No, but then you will have, so in standard geohydro, there's the problem that the stellar surface, the outside, well, you don't know what to do, like mixing between the two, so everybody just sort of does some dirty hack there. You have the same issue.
For
like a joint
in boundaries, you will have the same issues, yeah, sure. That's for sure. But it's not
theoretically
related to
it's
this.
worse, right? Because then you just try to convert a single equation in.
No, but you just put a parameter, that parameter big enough, so that you don't get into this point.
So you
And we explore the parameter. If we go out of the equilibrium, this parameter changes the place where this problem is, it changes, it's not fixed. You know how to change we were hoping that it will be fixed, so then we can make, okay, take a theory that just stays it. But if we change any of the parameters of if we go out of the equilibrium in any direction, we see this parameter moving. So it's not really that's up. At this point in the parameter space, there is another theory. It's moving. But that's an interesting problem. You can reduce the system.
If you enjoyed the video, like and subscribe.